cube at -5 Celsius is placed on the table. So you have an ice cube placed on the table, 20 grams at -5 Celsius. So we're assuming that the atmosphere is at 20 Celsius. So then what's going to happen? The ice that you leave there on the table will melt, right? And then eventually the temperature of the ice will warm up, and then it will reach equilibrium with the room temperature. Okay? So we're assuming that the room is so large that its temperature doesn't change, it stays pretty much at 20. So what is the change of entropy of the ice, the room, and the universe? So one of the things we want to show in this problem is that the reason ice melts is because the entropy of the ice increases as a result. So the entropy of the ice should increase, the room maybe should slightly decrease, right? But overall the entropy of the universe should increase in this process. So we have here ds is dq over t. Okay, so what has to happen now? Or let's break it to the ice. So heat has to come into the ice from the surrounding. Okay, and then as the heat is coming to the ice, the temperature of the ice is rising from -5 to 0, right? From -5 to 0. And then after 0, the heat that comes in will melt the ice, right? And then after that, after melting the ice, then we're gonna take that melted ice and we're gonna warm it all the way to 20. So remember that number line that we used to draw? This is 0. So the ice is starting at -5. So we have to take the ice, take it all the way to 0, melt it, and then from 0 all the way to 20, right? So then the dq is equal to the mass of the ice times the specific heat of ice times the change in temperature of the ice over T. So this is while it's still ice. Plus, then we have to put in a certain amount of heat while it's at 0. So while it's at 0, the temperature is not changing. So then you have m ice times LF of ice over the temperature of the ice. So that one is at 0. Then we have to do MC water, because after melting, the ice will turn into water, right? So its specific heat will be the specific heat of water times the change in temperature over T. So then we have to now integrate this. Okay. Delta S of the ice. So M of ice, specific heat of ice. And then this one is ln of. So from here to here, the final temperature is 0, right? Which is 273.15. The initial temperature is 268.15 Kelvin, right? So then we have to do ln of 273, that's the final temperature, over 268. ln of 273 over 268. Okay, so in other words, what that means is that the entropy that it has here is higher than the entropy that it has there by the ratio of the ln of 273 to the ln of 268. Its entropy is higher there. Okay, that means it's warmer and the molecules are moving slightly warmer, so it has a bit more entropy, you see. And then plus, now we're putting in some amount of heat. This one is not actually an integral, it's just itself. So then you just do the mass of the ice was what, 20 grams. And the specific heat of ice would be what? We have to look at that. It's about half of the specific heat of water. 2.108 joules per gram. 2.108 joules per gram Celsius. So the gram will cancel there, ln, plus then you have 20 grams of ice. Then specific heat of fusion of ice would be 334 joules per gram. And then divided by the temperature of the ice, which is 273 Kelvin. So notice you can't put 0 degrees Celsius, down here. So then that's the increase in entropy of the ice when it goes from solid ice to liquid ice. Because liquid is more entropy, more chaos than solid. You see? So the entropy increases when it turns from solid to liquid. Okay, plus the mass of the ice, 20, times the specific heat of water now, which is 4.184, times ln of the 20 in Kelvin is going to be 293.15 over 273.15. So that's we added up all the change in entropies of the ice in the melting process. $31? 31.147. Joules per kilogram. No, joules per Kelvin. So that's the entropy of the ice when it goes from solid ice at -5 to liquid ice. Liquid water at 20, the entropy of the ice increases by 31. This portion of it is most of it. 24.455. So the entropy of the ice when it goes from solid ice to liquid ice increases by 24. So you see, out of the 31, most of it went into changing the phase. When you change the phase of something from solid to liquid, the entropy increases. Remember, what did entropy mean? What was the meaning of entropy? The amount of what? Disorder, yeah. So liquid is a lot more disordered than a solid, because a liquid can take any shape that it wants, right? And then a solid is more compact. You already know its shape is something, it's set. And then, of course, when you go from liquid to gas, should it go to even more disorder? Yeah. So, of course, when you go to gas, what's going to happen? Let's say you take 20 grams of water and you boil it. What's going to be the change in entropy? You're going to do 20 times the heat of vaporization of water, which is a lot bigger, right? 2,000 something, and divided by the temperature at which boiling happens. So this is going to increase to 373, right? But this is going to increase from 300 all the way to what? 2,000 something, because it takes a lot more heat to boil. So that means the increase in entropy of water when it goes from liquid water to gaseous water is a lot more than from solid ice to liquid water, right? So the entropy increases a lot more when you go to vapor. Okay. Let's see what else. Oh, okay, so now let's calculate the change in entropy of the room. Because the room is losing heat, so a little bit of the heat from the room is going away, it should lose entropy. So how much entropy is it losing? Delta S room. Then you're gonna do dQ over T, where Q is the heat that went from the room into the ice, and T is the temperature of the room. The big difference, however, with the room and the ice is that even though the amount of heat is the same, the numerator is the same, you see? In other words, the heat that the ice is gaining is coming from where? From the room. So the amount of heat that the room is losing is equal to the amount of heat that the ice is gaining. However, the ice starts out colder, you see? So it's almost like the room is here, the ice is here, they're changing heat to each other, right? In our case, the room's temperature actually is not gonna change. So this guy is gonna give this guy a certain amount of, it's almost like let's say a billionaire is gonna give a poor guy some money, let's say $1,000, okay? So he's giving him $1,000, and then this guy is gaining 1,000 to the point where now, you know, he doesn't have the same money as this guy, but let's say he can now do whatever he wanted to do. So he's going up, right? That $1,000 means a lot to this guy. So he's going up, and now he can go to education or do whatever. The billionaire, the 1,000 he lost it's not affecting him that much, right? So he's kind of staying the same. So now what's going to end up happening is that the entropy that this guy gained, the ice, is going to be a lot more than the entropy the other guy lost, because to that guy, the $1,000 he lost is not affecting him that much. That's exactly going to happen on the physical scale. So the dQ that the environment lost doesn't affect it because the temperature is higher. This guy is bigger. Plus, the other thing is the room doesn't even experience any phase shift. That even more. So how do we calculate that? So then we just add the mass of the ice times the specific heat of the ice times change in temperature of the ice, plus we add mass of ice times LF plus mass of ice, specific heat of ice, times change in temperature. Oh, this is water. Water. Over temperature of the room. So the difference is that for this, I don't need to do integral. Why? Because at the bottom is the temperature of the room, not the temperature of the ice. At the top is the temperature change that the ice is experiencing, because that tells you how much heat is going into the ice. You see? So then the delta S of the room is going to be 20 grams here times this guy, which is a 2.108, times change in temperature, which is from -5 to 0, which is 5 degrees, plus the 20 times the 334, which is the amount of heat that goes into the ice to melt it. Plus the amount of heat that goes into warming the ice, which is 20 times 4.184, times the change in temperature, which is 20. Divided by the temperature of the room. It's kind of weird, huh? For change in entropy of the ice is a complete different process. I need to integrate it because the temperature of the ice instantaneously is changing. But for the temperature of for the room, it's constant. All I need at the top is the total amount of heat that went into the ice. So mass of ice, specific heat of ice, change in temperature.
Are you supposed to change the temperature to Kelvin or keep it in Celsius?
Change in temperature can be Celsius or Kelvin. It's the same. When I do ln, I have to be Kelvin because it's a ratio of two temperatures. But delta T can be Celsius or Kelvin. Good question. So now I'm going to do 20 times 2.108 times 5 plus 20 plus. Okay, and now of course I'm going to put a negative in the front. Why? Because the room is losing entropy. The room is giving away heat. So the entropy of the room is going down. Negative, I got 29.215 joule per Kelvin. So the entropy of the ice is increasing by 31. The entropy of the room is decreasing by 29. What's the change in entropy of the universe? Increasing. That's why ice melts by itself when you put it. This is crucial. That's why you don't see, if I put liquid ice at 20 by itself, it doesn't all of a sudden cool, lose heat to the atmosphere, and then freeze and turn into ice by itself. In other words, if I take a picture frame, a movie of this event, and I play it backwards and show it to you guys immediately know that it's played backwards. Because in your mind, you already know that you can't have liquid water cool, freeze, and go to ice at -5. So in your mind, in history, you already learned that things don't work that way. Just since childhood, right? So this thing running forward in time, entropy of the universe has increased. So change in entropy of the universe, 31.147 plus -29.215. Now you say it didn't increase that much, yeah, but I only had 120 gram cube of ice. Of course it didn't increase that much, but in order for this event to actually occur by itself and reverse its direction, the entropy would decrease by -1.932. The second law of entropy doesn't say it will never happen, but it's just very unlikely for this event to happen and reverse direction by itself. Okay, now what if I take this same 20 gram of water, put it in an ice tray, put it back into the freezer, and let the freezer freeze it back into -5. Has that changed the entropy of the universe? Has the refrigerator changed it? You see, so I'm gonna take this, I'm gonna take so I come home, I see on the table a little puddle of water, and I go, oh my God, my wife or somebody forgot there's water there. And I go like this, I put it in the ice tray, go, oh, let me make an ice cube again. So I go like that, put it in the ice tray, put it back into my freezer. So now I freeze it back. So what have I done? I've decreased the entropy of that ice back down, right? But am I gonna increase the entropy of the universe still? The answer is yeah, because there's no refrigerator that's 100% efficient. That refrigerator is gonna dump heat back up to the kitchen, right? So even though I'm gonna try to decrease the entropy of that ice, turn it back into solid ice, I'm still gonna increase the entropy, okay? So you could say if you put this ice water back into the ice tray, so I like this question because we're now reversing the order of that problem. We're saying you get that little puddle, you put it in an ice tray, you put it back into the fridge, and what is the change of entropy of the ice water? So now you put it into the little ice tray. Let's say it occupies one of them. Here's, you put the puddle there. Put it into the fridge, into the freezer compartment. Okay, so how does a fridge work? Remember, fridge is opposite of a heat engine. So you have T hot, T cold. You put in work in. You suck out heat from the cold, and then you dump heat to the hot. So let's assume the problem has to tell us what the coefficient of power of the refrigerator is. Coefficient of power of the refrigerator in the cooling mode is gonna be, let's say, some number like 6. That's a pretty good refrigerator. So its coefficient of power has to be given. So for refrigerators, what they do is they count how much cold heat you can extract from the cold, QC, divided by how much work you need to put in. That's how its coefficient of power is defined. QC over work in, that's 6. How much energy you're extracting from the cold. divided by work. Okay, where am I going with that? Okay, so what's the change of entropy of the ice water? Can we do that? Well, with the ice, it should be the opposite of the change in entropy when it melted, right? Because we're just reversing the process. So the change in entropy of the ice water, because we're gonna go back down. Yeah, so I don't have to redo that if I've already done that from example 1. What was the change in entropy of the ice when it warmed, when it melted, and when its temperature went up to 20? Well, now if I reverse it, it's gonna be the opposite of that. So 31, right? So it's now gonna be negative 31. Negative
147.
31.147. Okay, so now I have to calculate the change in entropy of the room. To do that, I need what? How much heat I'm dumping into the room divided by the temperature of the room. Right? How much heat I'm dumping into the room over the temperature of the room. Oh, okay, so now from here, from energy conservation, we have W in plus QC is equal to QH, right? W in is how much work you're putting in, plus QC is equal to QH, right? QH is what? How much heat you are dumping into the room, right? Q room, because that's going to be the room right here. All right. Now from here we have what? QC. Oh, we're going to have what? Work in is equal to QC over 6, right? Work in is QC over 6. Substitute that into here. QC over 6 plus QC is equal to Q room. And what does QC mean? It's the amount of heat that you're extracting from the ice to freeze it back down. You see? So that's how much heat you're taking from the ice and how much you are dumping into the atmosphere. You see? So then what does this tell you? 7/6 QC is equal to Q room. Okay, so now whatever you're taking from the ice, 7/6 of it you're gonna have to dump into the room in order to freeze it. I see what's happening. You're taking a certain amount of heat from the ice to freeze it. 7/6 of it you're gonna have to dump into the atmosphere. Okay, where are we now? What's the final thing? Okay, so Q room is gonna equal what? 7/6 of QC over temperature of the room. If I do this correctly, what should happen? The change in entropy of the room should be a positive number and should be larger than negative 31. Right? If it's a positive number and less than negative 31, such as positive 30, that means putting in an ice tray into the refrigerator reduces the entropy of the universe. That can't be. You have to still increase the entropy of the universe. Okay, so now, what's the QC? How much heat do I put into the refrigerator? How much heat am I extracting from the ice? Well, we've already done that. It's M ice, C ice, delta T plus M ice LF plus M water, C water, delta T over temperature of the room. In other words, that's what we calculated in the first problem as being 29 something, right?
Mm-hmm.
29.215. In other words, that's what we calculated in the first part as being how much heat I take from the ice and then divided by the temperature of the room. But I have to multiply that by 7/6 now. I got it. So exciting. Oh, God. Oh, man. I live for this. 7/6 times 29.215. 34! Yes. Positive 34. .08. That means the change in entropy of the universe is what? Positive 34.08 minus 31.147. Positive 3 something. So how good of a refrigerator do you need to have so that it doesn't happen like that? What if your coefficient of performance was 20? Now it's real good refrigerator. Are you able to now decrease the entropy of the universe? Put 20 here, what happens? Work in is QC over 20. Now you have to put in less work. That's actually good. You have to put in less work to extract this certain amount of heat from the ice. So that's a much better refrigerator. But if you put here 20, then what happens? 20 over 20, 21 over 20. So now you get 21 over 20. Now we might get close, but still the universe will not allow it exactly. 21 over 20 times 21 divided by 20 times, oh maybe, 21.2, 30.6. Ooh. Now actually the entropy of the universe decreases by placing it. But something else has to go wrong. Doesn't make sense. Maybe to make a refrigerator that good, you got to do something else that affects something, you know. Yeah, basically, if everything else goes right, and you have a refrigerator that is that good of 20, you could decrease the entropy of the universe by placing something in the refrigerator. But something else is going to go wrong, you know. I don't think there is a refrigerator that high. See, 12.6 is the best one for refrigerator keeping an inside temperature of 4 in a room at 29. Oh, remember that, there's another rule that the best the refrigerator can be is the Carnot efficiency. So I'm not even taking that into account. And the Carnot efficiency depends on what? The temperature of the outside and the temperature of the inside. You see? So I can't just say, let's create a refrigerator that is coefficient of performance 20, And then the outside temperature was, we were assuming was what, 20, right? 20, and then the inside temperature we were assuming was -5. Well, maybe you can have a refrigerator with a coefficient of performance of 20 with outside of 20 and the inside -5, because the coefficient of performance depends on the temperature of the outside and the inside. So it's like a cycle and it still kills you. So they're saying the best you can do if the outside is 22 and the inside is 4 is a coefficient of performance of 12.6. You see? So that in and of itself would limit you. Okay, so in these two examples, you see cases where entropy will be used or can be used in a problem such as calorimetry, in mixing ice with water, or mixing any kind of couple things. You can say, what's the change in entropy? Like you can go back to any of the previous problems we did. The calorimetry problems. The 140 grams of lead at -10 is placed in a container that has 200 grams of steam. What is the final temperature? What would the answer be if the lead had a mass of 50, right? And then we can add a question C to it and say, what is the change in entropy of the lead? What is the change in entropy of the water and the universe? You see, so you would do the same kind of calculation that usually involves an ln, mc dt over t, and you integrate it, you get an ln function, right? And then what you notice is that the one that's warming up increases its entropy. So in the case of the lead, it warms up, it increases the entropy. The one that cools, like the steam, will lose its entropy, right? But what will happen is the one that gains will increase entropy more than the one that loses, because it's starting out colder, right? So at the end, the total loss and gain in entropy should be gain, right? So the entropy should be gain. So you can do that to any calorimetry problem. And you could also do that to any thermodynamic problem. You can see here in the test so these are some of the examples for the Otto cycle in the test review and the Carnot cycle. Notice here it says, what is the change in entropy from state 1 to 2, from state 2 to 3, from state 3 to 4, from 4 to 1, and the total change in entropy. So for each state, remember what we were asking? What's the work done by the gas? What's the change in energy of the gas? And what's the heat into the gas? We can now add another question and say, what's the change in entropy of the gas in each state? So if we go back to the diesel problem, for example, and say the change in entropy in stage 1, change in entropy stage 2, change in entropy stage 3, change in entropy stage 4. Entropy is going to be similar to energy in that after I find each individual one, when I add them, I should get 0. Okay? So let's go back to that problem and say, let's add that portion and say, what's the change in entropy in each stage? Delta S1, delta S2, delta S3, delta S4. So now, what equation do we use? We say ds is dq over t. Now, for adiabatic, that's one of the simplest because there is no heat exchange, and so the entropy is the constant. You see? So entropy is constant. So delta S1 is 0. Remember when in one of the pictures he was showing, if we do PV diagram and we do a diagram of temperature versus entropy, what should happen? He was saying that adiabatic should be what? Constant entropy, right? So it was like this. Like that. You see? So that's the first stage. Now what's happening in this state? And change in entropy in stage 2. Is going to be what? dq divided by t. So for isobaric, what's the equation for dq? For isobaric, what's the equation for dq? NCP delta t. NCP delta t. This is second stage over t. You see, for this one, change in entropy, NCP delta t. Now if I integrate that, what do you get? NCP ln of T2 over T1. Now, if I wanted to graph the temperature versus the entropy of that state, how would that look? T versus S graph of the second stage. Then raise both sides to the power E, right? And I should get what? E to the delta S. Then you get what? This one goes to the power. In other words, this one goes to the power here. And then E and ln cancels. Then you have T2 is equal to T1 and CP, or you know what? Go 1 over NCP, 1 over NCP. So then you have here T2 over T1 is equal to E to the delta S over NCP. T2 is equal to T1 E to the delta S over NCP. So it's an exponential function. This one is an exponential function on the T graph. T versus the entropy graph. T2 is T1 E to the delta S NCP. Nice, 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 nice. Now what's left? Oh, then the delta S3 is also 0, right? So then that goes down. The entropy is constant. This is the second stage, this is the third stage, right? Like that. How about isovolumic? delta S4 is gonna be what? Delta S4 is gonna be, NCV, right? NCV delta T over T. So then integrate. So delta S for NCP ln of T, four, this one is T1, right? T1 over T4. NCV, sorry, NCV. And of course, this one is gonna be exponential also, exponentially coming back. Now, if I add up all the entropy changes, what should happen? 0, right? So what are the entropy changes here? Well, these two, there's no entropy change. Delta S1 is 0, delta S3 is 0. So these two should cancel each other, right? So if we call this 1, 2, 3, 4, delta S2, which is NCP ln of, you know what, let's call this T3, T3 to T2, ln of T3, T2, and then this one is delta S4 is gonna be NCV ln of what? T1 over T4. If I add those, they should cancel. So in our case, it would be CV was CP is 7 halves R ln. What was T3 in our case? You can just go grab the T3. $575. Was that this one?
658.
600? 50?
8.84.
Okay, and then divide it by the temperature here.
368.84.
Okay, that's the change in entropy from here to here. Now the change in entropy from here to here is gonna be in 5 halves R ln of this temperature.
255.
Hmm?
166.
Over.
575.71.
Okay. When I add that, I should get 0. If I did it right. Change in entropy should be 0, because these two are already 0. We've been on this a long time today, entropy. You could keep going on entropy, on and on and on, but I do want to get into electric fields and forces. So we'll end this and change topics. Something new, refreshing. Change is always good. I'm getting here,
Pastor, how did you write the NCP?
let me see. Oh yeah, 2.03. I was like a little unsure because this ratio looked smaller than that, so I was like, how is that gonna come out? And this is 5 halves, this is 7 halves. They canceled. Total entropy 0.
There was a question.
Yeah. Question? Oh, you got it? I got so excited that you don't want to put a damper on that, right? Excitement. I'm like, oh yeah, whatever. He's excited. Let's just go with it. You gotta just love this stuff, man. Woo. So good, man. You live for that. Okay,